Welcome, everyone. Welcome to Tap It, Shake It, Fling It, Chip It, the gesture animation dance. For those who don't know me, my name is Nicole Terc. I'm an Android GDE and also an Android tech lead at HubSpot. And you're going to be able to find these ramblings and some other more in my GitHub profile. Anyway, with that out of the way, let's go over what we're actually going to be doing today. And the answer, of course, as it should always be, is we're going to be making some dancing chip. And in order to do that, we're going to be using three things. We're going to be using animations, we're going to be using gestures, and we're going to be using sensors. So let's go over our chip strategy. In this talk, it's going to be pretty straightforward. The only thing we're going to be doing is we're going to be grabbing some information from gestures, some information from sensors, and grabbing that data to create some fun animations. And that's it. So let's just hop on in and start with some animations. And the part I want us to focus is how do we actually need to do what do we actually need to do in order to make some animations? Whenever I'm thinking of making animations, I normally follow the process of answering three questions. And those questions are what, when, and how. What properties do I want to animate from this view? When do I want this change to happen? Do I want it to happen whenever I click something, whenever I fling it, whenever I do anything with the screen? And how am I going to actually do these changes? Like changing sizes, changing colors, moving them around, whatever I want is described there. Once I have a function animation that sort of does what I expected, I normally add a fourth step. And that is basically just play around, click things, see what happens, and have fun. So this is all well and everything, but what are we actually going to be using in order to make these animations? The answer, of course, is some animation APIs. So if you haven't done already, I highly recommend that you take a look at the Jetpack Compose animations documentation, where you're going to find all the animation APIs explained, and also our trusty flowchart for picking which animation API to use. I know it looks big, I know it can look overwhelming, but this is the second version, and it's pretty good. You just need to start from the start, follow it all around, and you're going to reach the space that you're looking for. Which in our case, since we're going to be working with gestures, I have the answer right there. I need to use Animatable, which is a coroutine-based API. Cool. I think that's all the theory we need for now, believe me. So let's just drop all these words to the side and let's dance. Small disclaimer before I continue, by the way. This chip is a canvas. So everything you're going to see here, you can replicate using some other cool stuff like, squares or text or circles or your favorite composable. But for now, I'll stick for the chip. They kind of are in the title already. So let's go and animate some gestures. In order to start, slow, because we're just starting dancing, let's do a classic. Let's do a tap dance move. And in this case, let's do tap to scale. As I said before, the process is just answering three questions: what, when, and how. And in this case, it's pretty straightforward as well. We're going to be changing our scale whenever a user taps on it, and we're just going to be toggling it from 1 to 1.2. These values are arbitrary. I just randomly picked them. I encourage you to just play around and see which numbers make sense for you. But let's translate this to code. An initial implementation of changing scale in my chip could look like this. We're basically going to define a scale float value. We're going to pass that scale value to our graphics layer. Important point here, remember to use lambda modifiers whenever it's possible because you don't want to have a bazillion of recompositions, especially with animations. Anyway, once we have our scale in there, whenever I click on this chip, I am just basically going to get our new scale and update it. Cool. If I run this code, the chip is already scaling. But there's a glaring issue here. And that is that we actually aren't animating anything yet. So let's fix that. Since we said we're going to be using animatable according to our trusty flowchart, the only thing we need to do is go back to our scale and change that float value to an animatable. Since this is no longer a straightforward float, whenever there's an update to this value, instead of doing a direct assignation, we need to call animate2. And of course, wrap it in a coroutine, because as I said, coroutine-based API. Anyway, I only changed like 3-4 lines, and just doing this and running this code, you're going to get an animation. That is it. As you can see, adding animation APIs to already existing code is a piece of cake. So you no longer had an excuse to avoid them. Just make sure you animate everything from now on. But this animation still looks kind of plain. Let's play around with it. In order to do that, whenever I'm trying to make my animation a bit different, I just beeline to animation spec. Now, I'm not going to go too deep into this. The only thing you need to know is that this animation spec is an optional property in most of the animation APIs that is going to let you change how this animation is going to play. You, again, don't need to write anything. There are already a lot of animation specs out of the box that are going to make your animation look totally different from one another. We have Twin, which is a time-based animation. We have Spring, which basically simulates a spring. And we have keyframes, one of my favorite, which basically is going to let you define the key frames of the animation that your view needs to hit. But anyway, I ramble. Let's go back to our example of the chip that scales. And in this case, let's change this to basically a spring that is going to have a high bouncy ratio and a really stiff way to see. I don't know. It's just going to duplicate that. And the cool thing is by just changing those 3 lines, my animation is going to be totally different. Look at that. Looks cool, right? And of course, that's not the only thing you can do. You can basically play around with all the animation specs that are around, and you can have your same scaling chip, but scaling it in a different, unique way. Cool. I think that's it for our tap to scale. So let's go to our second dance step, reposition. Because someone once told me that whenever you're dancing, you're supposed to move around the dance floor, not stay in one place. So let's do that same thing for our chip. So what are we going to be doing here? We're going to be changing the position of my chip. In this case, whenever you're thinking in position, you're actually going to be changing translation, words, the same thing. And we're going to be doing that whenever I drag around this chip. How I want to animate this is going to be pretty straightforward as well. I just want to make my chip go to wherever my finger is going. Cool. Let's translate this to code again. The code, and that's all of the code, is going to be this. We're going to create again our property, which is the thing we're changing. In this case, we're going to be using an offset animatable. And for that, I will need to pass our vector converter, because there is no out-of-the-box constructor for animatables with offsets. No matter. Everything here, as I said, is out of the box. These vector converters are also available. So if you want to animate something that is not your IDE is complaining about, just check if the vector converter is already available. Anyway, once we have this translation, we need to again update our graphic layer to change the translation of the chip. And in order to receive all those gesture dragging events, we're going to be using the modifier draggable2D. There are other draggable modifiers that are going to help you when dragging horizontally and vertically just in one direction. But since I'm moving all around the screen, I am going to be using the 2D or two-dimensional one. Now, the only property I need to pass this is the draggable state, which is basically going to be the one that is going to be updated whenever this chip is dragged. And in here is where the changes are going to happen. This draggable state is going to return me the delta, or the change where the finger moved. And according to that, the only thing I need to do is animate mass translation. Important thing in here is that I am not using animate2 in this case. I am using snap2. And that's something that you're going to see in some animations regarding gestures, because we don't want to slow down the reaction of my chip whenever I'm dragging my finger. I want the chip to be right away where my finger is with no delay. That's why we're snapping right into it, which is basically going to ignore all animation values and just move there. Cool. So just as a rule of thumb, whenever you're doing a gesture that needs to be following the finger of the user, use snap2 instead of animate2. You're going to thank me. It looks really weird. Anyway, and that's all the code, literally. I just copy-pasted from my repo. So if you run this code, you're already going to have a dragging chip. Thank you. And I think that's it for dragging. But dragging is kind of boring. It's just moving there, and yeah, it's already doing things and having fun there, but let's do something more with this. And for that, let's go to our third step. Fling and back. Again, answering our three questions. What am I animating in this case is the position again. I'm still moving my chip. But now, instead of just dragging around, I am going to be doing a fling. If you have ever scrolled in a list in your phone, which I hope you have, whenever that list goes and overshoots, that's a fling. So we're going to detect those, and whenever I detect this fling happening, if my chip ends up outside the screen, I'm just going to move it back. Cool. So let's translate this to code. And in order to do so, let's go back to our draggable as we had before. This is the dragging code as before. You need to use that. And the part we need to change is actually that draggable to the modifier. You see, the state is the only thing you need to pass, but it's not the only thing you can pass. In this case, we're going to take advantage of a second parameter called onDragStopped. It receives a lambda, and basically it's going to be triggered that lambda whenever the dragging finishes, or when the user separates the finger from the screen. Cool. Once we get this, we're going to be calculating our fling move, which is basically where our chip is going to dance. So how does this fling move look like? It looks like this. I know, a lot of words, and here's when maths come into play. But don't worry, let's break it down. It's actually quite easy. The key thing on fling moves, or any gesture that requires calculation of future positions, is decay. Decay is going to help us calculate, or basically, calculate the future position or value of different properties according to velocity. So it's going to tell you how your animation is going to be decaying across time. Now, what we need to do here is grab the decay, basically use it to calculate the future value where my chip is going to be dragged to. Important thing, this is just calculating things. We're still not animating anything. And according to that value is where I'm going to check. Is my chip still inside the bounds of the screen? If so, we're just going to animate that decay using the trusty and helpful animate decay out of the box. If my chip is not inside the bounds, it means that it's already overshoot outside of the screen. That's where my fun animation is going to happen. And in this case, as I said, we're just going to let it go and then back. So this is what we're going to be doing. In this case, we're going to be using animate to because my finger is already out of the screen. So I am going to grab the target offset that I had, and I'm going to animate all the way I can until I reach the borders of the screen, and after that, I am going to animate back. Something powerful about this coroutine animatable API is that it's going to let you really have control of your animation. In this case, by calling first the animate outside of the borders, my chip is going to go there. And after that animation finishes, it's going to trigger the second line, which is going to go back to 0. So it's going to target one animation right after the other, no delays. Cool. So that's all the code. As I said, it looks scary, but it really is not. And by doing that, we already have our fling move. We're flowing through. That's really easy, huh? You should all flings everywhere as well. Anyway, with this, I think we're done with fling and back. If you want to play around with this, you can, of course, change animation specs and add more things. But for now, I think you get the idea of where I'm getting at. So I say that's it for gestures as well. Let's jump into something more sensory. And let's start with sensors. Now, whenever you work with sensors, there's also going to be a process. Regardless if you're working with animations or working with anything else, the steps that you need to follow, or at least I follow, are this. First, I will need to pick a sensor, which we have a bazillion of them. Well, not a bazillion, more like 20. But you're going to get everything documented in both iOS and Android. And after picking the sensor you want, you need to listen to that sensor data and consume the sensor events. Now, I am not going to go super in deep on this. There's a lot of documentation online that you can check. But the important thing I want to call out is that these sensor events are going to be, of course, different for each sensor. So that's something that you will need to understand before starting to work with them. So for example, if you're working with gyroscopes or things like that, you're going to receive rotation coordinates. But what are those? What does it mean? And of course, if you're working with something else like temperature sensors, you're going to receive temperature in degrees. So that's something to keep in mind whenever you work in sensors, as I said. But how are we going to be using these sensors in my chip dancing project? The plan, since of course we're using multi-platform project, is we're going to create a multi-platform sensor manager. Sadly, this multi-platform sensor manager is not going to have a lot of shared data because iOS and Android tend to receive sensor data differently. So in order to create this multi-platform sensor manager, we're going to need to have an Android sensor manager and an iOS sensor manager. Cool, but let's translate this to code so you get a better idea of what I'm talking about. An easy implementation of this multi-platform sensor manager is basically to just create an interface. In this case, we're going to create it in main. We're just going to call it, because I don't have creativity for names, multi-platform sensor manager. And in there, I'm just going to define two functions. Register listener, to whenever I want to register a new listener for any sensor I have, and unregister all. This method is really important because the sensor managers are going to be drawing you data until you register your listeners from it, regardless if your application is in foreground or background or close to. So if you don't register your sensor listeners, your users are going to hate you because their battery is going to drain. So anyway, cool. Once I have this interface defined, an easy way to start creating this for iOS and Android is basically create an expect function. In this case, if I'm working with Compose, I can just create an expect function composable that is going to remember the sensor manager. Of course, you can replace this with your favorite dependency injection framework for this, but for an easy implementation, this works. The only thing that is needed to be done is, after having this function, we of course need to create the actual implementation of this remember multi-platform sensor manager in both Android and iOS. And each of them are of course going to provide its own implementation of both Android and iOS. Cool. So far so good, but let's take a deeper look on how these sensor managers for Android and iOS look like. And let's start with Android. The way Android works with sensors is you're going to need to create an instance of sensor manager. Now, this sensor manager is a system service that basically you're just going to get from it, like a regular service from Android. You're going to probably have to provide some permissions in the manifest in case you want to get some delicate data. But after doing that, if you want to register a listener to that sensor manager, the only thing you need to do is get the default sensor manager. Get the default sensor that you're looking for. And if that sensor exists, you can just basically register the listener to it. And with that, you're going to start getting data. That's it. Pretty easy. Now, for unregistering things, the only thing you need to do is for each of the listeners that you are registering here, you will need to unregister them as well. Of course, I'm omitting some lines in here, so that's why you're seeing some incongruencies there, but I invite you to take a look at the code if you want to see the full implementation. But the gist of it is like this. You get your sensor manager, the one from Android, the real one, you just register things to it, and when you're done, you just unregister things. That's it. So let's take a look at how iOS does things. And something that I found surprising when I jumped here is that in contrast to Android that only has one point of contact for sensors, iOS actually has one manager depending on the type of sensor that you want. So in my case, if I wanted to get some motion information, I will need the motion manager. If I wanted to count steps, I needed the pedometer manager. If I wanted to know if my user was running or swimming or doing things, I needed to get the activity manager. And if I wanted my ambient lights, I need a sensor reader, which is a new sensor kit, which actually you need other things in order for that to work. And each of these managers have a different set of permissions and things that you need to set up. And I am not going to delve into that, but I invite you to take a look at the repo. So anyway, of course, since we have different sensor managers that are going to be providing different information for the sensor, whenever I'm registering a sensor, I need to check what type of sensor I am going to be getting, and depending on that, do something different. And I say something different, but actually most of these sensors follow the same approach. So let's see an example with accelerometer. So if I want to get my accelerometer information, this star accelerometer updates will look like this. I am going to get my motion manager. I am going to check if the accelerometer is available. You see, similar to the Android one, just check if it's there. And if it's there, I am just going to start observing those updates. The same approach is going to be, this approach is going to be the same for all the other sensors in iOS. So it's pretty straightforward as well. It's just bothersome to create 10 for the same thing. But anyway, of course, whenever you need to register sensors in this case, you again will need to go over all the managers and all the things that you started, and then just finish them all. But that's it. It's a bit more worthy, but at the end, it's the same approach. You just get your sensor. If your sensor is there, just register a listener, and when you're done, just unregister. But something important to note in here as well, I forgot to mention, is that this sensor kit requires a paid Apple developer account if you want to change it, because you need to provide a provisioning profile. So just keep that in mind if you want to play with ambient light. I found it the hard way. Anyway, with that, we are done with Sensor Manager. So let's start dancing again. And for that, let's start with our first sensor step, the rotation shift. This rotation shift, again, we're going to need to answer our 3 questions. Our what, we're basically going to be changing our rotation of the chip. Our when is we're going to be changing it whenever the orientation changes. And our how is basically we're going to grab the same change of orientation and duplicate it in our chip. Cool. Now, there's a small catch on this, and that is that there's actually a 0 step whenever you work with sensors. As I mentioned before doing anything with sensors, you need to actually understand the sensor data you're going to be getting. In this case, orientation. So let's take a look at how orientation sensor data looks like. And let's start with Android. If you check the documentation, you're going to reach a point where you can summarize it like this. Whenever you listen to orientation inside the Android Sensor Manager, you're going to get 3 values. Azimuth, which is basically the Z rotation in your screen. Pitch, which is going to be the X rotation in your screen. And roll, which is going to be the Y-axis rotation in your screen. They're going to have different ranges, and they're going to be having different ways of calculating this, because actually orientation is no longer a sensor, but I ramble. But this is what you're going to get. Cool. Let's take a look at iOS. In the side of iOS, you're going to have something similar, but not. We're going to have yaw, which again is our Z-axis rotation. We're going to have pitch again, which is going to be the X rotation again. And we're going to have roll, which is our Y rotation. But of course, if we put them side to side, it is glaring to see that they are not the same. So what do you do when you encounter these things? Don't worry, the fix is easy. You're basically just going to grab one, in my case Android, because of course I started doing the Android things, and then you're just going to map whatever values from the other platform to that. And in order to do that in the easy way, you can just create in your shared code a shared data class, which in my case was just called device orientation that returned azimuth, pitch, and roll, and some helper methods in there. And because I was feeling lazy and I didn't want to do all the mappings for my register listeners and things like that, I just created another method in my multi-platform sensor manager called observe orientation changes. That was going to be in charge of getting all this orientation information, map the things, and make sure that I would always get a device orientation in the correct values. Cool. But that's it for understanding orientation. We're already changing a bit of the code, we're already adding all the things, we're ready to start adding this azimuth thing in our chip. So let's see some code. Starting again, we need to define the properties we are going to be changing. In this case, I am going to be changing rotation in X, Y, and Z, all the axes in my chip. Once we have that, we're just going to update it on the graphic layer, which it's already there, so I don't need to calculate anything, I just need to pass the values. And going into the how, this is where our sensor manager is going to come into play. The only thing we need to do is get a reference to our sensor manager. Once we have that, we're just going to observe our orientation changes where all the heavy lifting is happening, so I don't need to use it in my UI. And once we have that orientation, I just need to update my rotation. Important thing in here, I am triggering a different coroutine for each of them, And that is because I want these changes to happen at the same time. If I put them one after the other, I would end up like with the flinging move, where one would happen first and then the other. I don't want that. So triggering them separately is going to ensure that these rotations are updated independently. And of course, I'm using snap, because this rotation needs to go snappy. So once we have that, we just need to pass our orientation values on degrees. Important thing in here, our modifiers expect degrees, not radians. So be careful on that. And with that, that's it. We have a rotation chip. Thank you. And if you're wondering what I am using right there, that's basically on Android Studio. You have a sensor emulator that is going to let you emulate different sensor values. They also have like temperatures and humidity and things like that, so I highly recommend you to check that. You just need to click on that three-dot menu and move to sensor emulator. And also another note on this, now that I'm talking a nice Android Studio, if you want to do the same on iOS, I am sadly going to tell you that it's not possible. There's no sensor manager emulator in iOS, so you will need to get a physical device that is enabled for sensors, because your iPad is not. Anyway, I think that's it for my rotation shift. Let's go into Shake It, our next dance step. Again, we're going to be answering our questions, and this is what I'm going to be doing. I am going to be updating rotation, translation, and scale whenever I shake my device. Now, how I'm going to be doing this, basically when a shake is over, I just want to side my chip side to side and have a nice and wiggle. Of course, as before, we'll have to have our step 0 here, which is going to be understand the sensor data. And in this case, the one we're going to be using is accelerometer. So how does this acceleration data looks like? Let's start again with Android. If you check in the documentation, you're going to find things like this again. Yes, they like to reuse that image. We have our x-axis acceleration again, our y-axis, and our z-axis. But in this case, instead of getting rotation degrees and things like that, we're going to see how is the acceleration changing in those axes whenever I move my device. Cool. So far, so good. Let's move into iOS. If you check the documentation, you're going to find that they're actually exactly the same. So for once, there's nothing that we need to do in order to consume this acceleration. We're good to go. We can use our usual register listener inside our multi-platform sensor manager. So let's see some code. Again, we're going to define our properties. In this case, I am going to be changing scale, our rotation in C because it's rolling like this, and our translation because it's moving side to side. Once I have that, I just need to pass it into our graphics layer, and to the how, this is where the sensors again come in. The first step is basically we're going to register to our listener, which in this case is going to be acceleration. We're going to get our X, Y, and Z, and the last part is where the calculations are going to happen. And the important part in here is that instead of like jumping right into it and do things, is first check online if someone already did this and just adapt it to your code, which is what I did. And there was a nice solution that I liked that was simple enough to explain, and that's basically what I adapted in this place. Of course, there are other ways to do this, where, like, you know, go deep into the math and start calculating things and get some sampling things, yada, yada, yada. But for now, in this example, this works. So let's break it down as well. This solution, what it's getting is basically getting the magnitude of the acceleration vector. That means, like, if you're moving it in different directions, this is going to get you the value of that. After that, we're accumulating our acceleration to get the acceleration values for that. And just checking a magic number that is going to be how sensible you want the shake to happen. And if that acceleration is measured to this magic number, it means your device is shaking. If it is not, it means the shaking has finished. There are, of course, more lines, less lines that you can add in here, but as I said, go play with the repo. I highly encourage that. And now that we're doing the shaking things, different from the rotation move, instead of like replicating this rotation, what we want is, whenever this finishes, we're going to be doing the shake move in here. So we're using the shake like a gesture, and when it's done, we do things. So how does this shake move look like? It will look like this, a regular animation, because I am actually not using anything from the sensors besides the trigger to create that. So this is what I'm doing. I am basically creating, again, a separate coroutine for each of the properties I'm changing, translation, scale, and rotation. And inside of that, I'm, of course, going to be using keyframes because I want to move my chip side to side. And a small tip in here, if you're going to be doing different changes for different properties, and you're a bit lazy like me that don't want to create those transitions things and update things, one thing you can do is basically ensure that all your keyframes have the same duration and are triggered independently, so they just basically start and finish at the same time. So that's it. But for the sake of showing you a little bit how these keyframes will look like, they will look similar, all of them, let's take a look at the rotation. In this case, the only thing I am doing is defining which value I want at which point of the animation. So I am passing from 0 at the beginning to 180 at 1/4 of it, then back to the center, then to the other side, and back to the center. And that is also why my target value ends up being the same as the initial value, 0. Cool. And with that, we can basically do the shake thingy or the animation that it looks like. But we're still missing the little wiggle, right? Don't worry. In order to add that wiggle, the only thing we need to do is add even more keyframes. And that's it. You just need to make sure that you're triggering them one after the other. In this case, I don't want it wiggling and moving at the same time. But with all of this, we already have our shaking chip. Which, of course, you need to shake correctly if you want it to move. There you go. That's it. And with that, I say that's it for the shake it. And with the shake it, we already have them all. You can tap it, you can shake it, you can fling it, you can chip it. But of course, you don't need to finish it right there. You can create your own dance moves and get wild. You can spin it, you can pick it, you can dim it, you can step it. You can just basically grab whatever sensor you want, whatever gesture you want, and just animate it. That's my excuse anyway. But for now, I think that's it. Thank you. If you want to learn more, I highly encourage you to take a look at the code and also take a look at the videos from animations from Rebecca Franks. There's a lot of documentation as well in both Android and iOS regarding animations and sensors that you can take. And yeah, that's it. Thank you. And don't forget to vote.